let us continue our session, and the remaining 3 talks will be more closely related with groups, and it is my pleasure to present the next speaker, Andrey Vasil'ev, who, in my eyes, is one of the leading researcher in the theory of finite groups. Andrey, please.
Thank you, Ilya. The subject of my talk is closures of products of permutation groups. And the main goal is to present a new and precise formula for the closure of the rest product of two permutation group in product action. My talk is based on our joint paper with Ilya Ponomarenko, our chair today. Well, and I will start with some basic definition by okay. If let us take some positive integer m, and we consider a permutation group G acting on a finite set omega, then the M closure of G is just the largest subgroup of sim omega among the groups, among the subgroups having the same M orbits with as same orbits as G initial group, where M orbits is just the orbits of the action of the induced action of G on M's Cartesian power of omega. Well, also M closure can be considered as a full automorphism group of M array combinatorial structure consisting of colored relation which are just M orbits of some group G. Well, and this provides us with the connection of the problem of finding or studying of M closure with the problem of finding the automorphism of combinatorial structures, the graph isomorphism problem, and so on. In this sense, and it makes it explains why the problem of finding of M closure is a non-trivial problem, not only from theoretical but also from the computational point of view. But today I'm in my short talk I am concentrating on some theoretical aspects of this problem. Well, the following chain of inclusion can be easily deduced from the definition, and it was done by Wieland. Actually, and in the sense of this chain of inclusion, we can consider M closures as some approximations of a group G. And so our question can be, general question can be formulated like, how far can be M closure from, can M closure be from initial group? Well, first of all, it's easy to observe that the M closure of M transitive group is a whole symmetric group. So the one closure can be very far from initial group, because one closure of transitive group is the whole symmetry. But in case when is greater than one, the problem is much more interesting, much more mysterious, and so on. It was shown by Wieland, who found who made some foundation of this theory, that if you take M greater or equal than 2, then M closure of abelian group must be abelian, and the same is true for the group of odd order and even for P group. It is also true for important group, but if we consider solvable group, then as far, well, it's easy to find examples of two transitive solvable group. And by our previous observation, if you take such a group of degree at least 5, its two closure will be the whole symmetry group, non-solvable. So in general, two closure of a solvable group is not necessarily solvable. But recently, we proved with Eamon O'Brien and Evgeny Vdovin that if you take m greater or equal than 3, then m closure of solvable group must be solvable. It's non-trivial actually result. And I will. What is the usual approach in proving such a result? Actually, this result was presented. This result was presented in the previous conference workshop in last November here. But today I would like rather to explain some how some reduction theorem can work here. Okay, but first, let me recall you some basic facts on M-closures. First of all, M-closure is indeed a closure operator. It's indeed a closure operator. All three properties. Okay, all three usual properties can be easily checked, verified. Well. The second, well, since this is M-closure, the M-closed objects are, of course, of special interest, and there is a very simple, sufficient condition for the group, for permutation group G to be M-closed for M greater than or equal than 2. It suffices that G has a regular order, at least one regular order. Well, and last but not the least fact is the so-called closure argument, or Wieland's closure argument. It gives you a necessary and sufficient condition for permutation, for arbitrary permutation in omega lie in the enclosure of group G. You take a permutation F, and it lies in M-closure if and only for every M tuple alpha. There is an element from initial, element G from initial group, such that its action on this tuple coincides with the action of element F. Well, now, as I said before, usual approach to prove theorems about properties of enclosures is to reduce the problem from arbitrary to transitive, from transitive to primitive, and so on. And in order to do this, we should know how closure operator relates with the products of permutation. So let us take two permutation group, K acting on the set gamma and L acting on the set delta. First of all, it's actually easy to show that if you consider a direct product of groups K and L, then it acts and consider its action on disjoint union of gamma and delta, then M closure for all M actually M, it's M closure of such a direct product coincides with the direct product of M closures. Well, it's really easy to show, and it's some well-known result. Well, but actually this is very useful result, very helpful result. Why is so? Let us say consider the case of abelian group. Well, since abelian group, transitive abelian group is regular, we know that it's too closed, it's enclosed for every M greater or equal than 2. And now, applying our proposition 1, we can reduce the situation with arbitrary permutation group to the case of transitive group, and then it's easy to show that the 2 closure or M closure for every M greater than 2 of abelian group is abelian. Well, by the way, the direct product of group K and L has another natural action, the action on direct product of the set gamma and delta, and in this case, the same formula also holds, but starting from M equal to 2. Well, maybe it's not so easy to prove. At least I'm not. I have not seen the real proof of this fact before, so I really. I would like to thank Dima Churikov, who includes the proof of this fact in one of his last papers. Well, now, but so in the case of abelian group, of course, it's enough to reduce the situation to transitive group. But in more general situations, like for say P groups, it is not enough, and so. We need to reduce situation, say, for primitive group, and we can do this by this the following result by Lev Kaluzhin and Misha Klin. The old result of Lev Kaluzhin and Misha Klin. They prove that if you take a rest product of groups K and L acting in primitive, so that is acting on the disjoint union of copies of gamma enumerated by elements of delta. Then again, for every M greater or equal to 2, the following equality holds. M closure of rest product is just equal to the rest product, in primitive rest product of M closures of corresponding groups. Well, but as in the case of the direct product, in the case of rest product, there is also another natural action of rest product of groups K and L, but on the now product of copies of gamma enumerated by delta, or by another words on delta's power of gamma, or is usually or in so-called rest product in so-called product action. Well, because it is of our prime interest, let me maybe in some non-standard way denote this special case like this. Let K up arrow L denote the permutation group induced by this product action of rest product on delta's power of gamma. Okay. Well, so our question was: does the same nice formula, same equality holds in this case? But in general, the answer, unfortunately, in general, the answer is no. What the simplest and at least the smallest example is the following. Let us take the rest product in product action of symmetric group of degree 2 and alternating group of degree 3. It is easy to check that to closure of such a group is just a rest product of two symmetric groups of the same degree. But if we consider the two closure of alternating group of degree 3, then it is equal to this group, because alternating group of degree 3 is regular, and we know if the group has a regular orbit, then it is too closed. So the rest product of two closures is just a symmetric group by alternating group of degree 3, and so we not have we don't have not only equality, we don't have even inclusion in the right direction here. Okay. Well, but this is let's see. This is well. This is bad news. The good news were obtained by in two papers. In paper in first of all, this is a result by Evdokimov and Ponomarenko. Again, old result. They prove that in case when m is equal to 2, two closure of rest product and product action is included in the rest product of two closures corresponding unless group K, the group K is to transit. Well, the case when m is greater than 2, say it is equal to 3, was of course considered in our paper, in the paper where we considered the question about solvability of m of 3 closures and of course for m greater. And we in fact proved what we need, or rather we proved what is enough to make next step in our reduction, because of course we can suppose there that this rest product acts primitively, and in this particular case we were able to prove the inclusion, but in fact it was done actually maybe about 2 years ago, at least this lemma. But after that, we continue to think about this question. We continue to think how the exact formula can look like. Well, and as I said before, my goal is to provide you with the exact formula. But let me remark that some partial results, in case when, again, this product is primitive, were also obtained by Prager and Saxon in his paper on closures of circles, on structural circles of closures of primitive group. But no exact formula also. Well, in order to present our result, I need to define another closure, again in the class of permutation group. So let us consider the set omega to the power of m in square brackets as the set of all ordered partition with the number of classes at most n. And again, group G acts on this set, and we can consider the largest permutation group having the same orbits as G in this induced action. And let us denote this by G to M in square brackets, and we call it closure with respect to partition, say. Again, for this new closure, the following chain of inclusion holds. It's again a closure operator in usual sense, and also the analog of Wieland closure argument holds, which is important. And actually, the application of these two closure arguments allows to easily actually prove the following inclusion. It shows that easy to show that m+1 closure with respect to partition, this group, is always a subgroup of usual m closure. But I need to skip to this detail because I don't have enough time here. Well, so now our main result. So let us take two permutation group and positive integer m greater or equal than 2. Then m closure of the direct product of this group in product action is always, does not depend on primitivity and so on, is always equal to the rest product of m closure of lower group K, and K closure with respect to partition of upper group L, upper factor L, where K is just the minimum between two numbers, degree of L, and the number of orbits of lower group, M orbits of group K. That's the exact formula. So now let me explain what this formula means in the case if we are interested in M closures, in usual M closures. In fact, using this theorem 1, it's easy to show that at least it's easy to prove the following theorem. Where we consider the structure of enclosure in language only of enclosures. So let K and L be again two permutation group, N again is greater or equal than 2. Then M closure of the corresponding rest product is included in M closures of K and L, unless M is equal to 2 and K is 2 transit. So theorem 1 covers at least all previous known results. Moreover, it doesn't require, say, primitivity of the rest product when M is greater than 3, and so on. Well, and is indeed a consequence of the theorem 1, because let us say what is non-trivial? Why is so? Why so? Let me explain it shortly. If K is equal to D in theorem 1, then actually this is not a K closure, it's just L, because as we see, if you take the if M is just a degree of initial group, then of course its M closure with respect to partition is equal to the group. So if K is the minimum, if D is the minimum here, then it's just an L, and our formula obviously holds. So non-trivial case when K is equal to the number of orbits of group of M orbits of group K. Sorry. And this number is bounded from below by the number of M orbits of the whole symmetric group. And it's easy to see that this number is greater than or equal to the M plus 1 if M is greater than 3 or K is not the whole symmetric group. So we may apply actually the inclusion from the previous slide here and get what we need. Well, this is maybe the most important consequence of our result, but we also can simplify this equality or make more precise result in the case when L is primitive group. Let us consider this. It turned out that if L is primitive and is not an alternating group in standard action, then our formula can be simplified. We can take here just a group L instead of its K closure with respect to partition. And this is because of the following fact. If you take any primitive group, and M, of course, here we need to also suppose that M is greater or equal to than 3. Well, here and in theorem 3 as well. Then M closure with respect to partition is equal to G, unless G is the alternating group in standard action. Well, of course, if G is the alternating group in standard action, then its M closure is just a symmetric group. If M is not greater than N minus 1. And this fact actually is based on the old result by Akash Servish, who classified all the pairs of primitive groups distant from the alternating symmetric group of same degree, such that one of them is a subgroup of another, and orbits of these groups on a power set of omega, on the set of all subsets on it as a state. He described all this group, and there are only a few of them. The degree of such group is less or equal than 10. So it's easy actually to check our statement for all these pairs, exceptional pairs. And this gives us this result and so theorem. Well, that's all. Let me finish with our main result, with the precise formula for M closure of the rest product and product action, and also the reference to our paper. Actually, when during the Gabar talk, I got the message from Springer that it is online. This paper now is online. So it is not only accepted, now it's published. Thank you very much.
Thank you, Andrey. And we have time for 1-2 questions, if they are, remarks or comments. Okay, I don't like to ask you some questions because I am a co-author in this case, and it would be unusual if I do this. Okay, let us thank speaker again, and we have 3 minutes till the next talk.